Yes, sir. Welcome in our lecture fact. Today we are going to discuss the summary of shunt compensation, entire shunt compensation. Now, in this summary, the detail of equations and derivations is not going to cover. Only the objective of shunt compensation, their location, and what are the advantage of shunt compensation in the transmission line is going to discuss. So what is the fact devices? The fact devices we are using in the power system to improve the power transmit ability of the transmission line, existing transmission line, and to improve the transient stability and steady state stability of the existing transmission line. Nowadays, the capacity of power plant is gone increasing, whereas the transmission capacity has to be increased with the same rate. So, but we found a difficulty in increasing the transmission capacity by laying a new transmission line, then acquiring land and all these things. So it is better to modify the electrical characteristic of the existing transmission line to enhance the power handling capacity of existing transmission line, which will improve the transient stability also. So our objective with the help of fact devices to modify the electrical characteristic of the existing transmission line to handle more power with a long distance, because it is found that as the distance for the EHV transmission line, it is found that going for this one, we will take the simple example is that if the capacity, if the power, say the operating voltage, say it is in kV, operating voltage, and the length of the transmission line in kilometers. So under such conditions, say the transmission line voltage is 400 kV, it may be a 765 kV, and say 1000 kV is the transmission voltage, and whereas the say what we can say that it is 200-kilometer line, that is say 400-kilometer line, and so on, say 600-kilometer line. Here on the horizontal, say for example here say 200 megawatt power, then because of increase in system voltage, it is increased to the 400 megawatt power, and say it is a 800 megawatt power. It is not a calculated value, just I'm just putting some random figure just only for the understanding. But as the distance of the transmission line increase, the power handling capacity decreases. Say it is 150 megawatt and it is say 100 megawatt. So we found that as the capacity, as the operating voltage increases, the power handling capacity of the existing transmission line can increases, whereas the for EHV system, as the distance of the line or the kilometer distance between two substations get increases, definitely the power handling capacity of the transmission line decreases. So this is the difficulty in the EHV system, and to overcome this difficulty, and we want the power handling capacity of the transmission line to be enhanced, then fact devices, it may be a series fact devices, it may be a shunt fact devices, or the combination of both is going to increase. So our basic equation, we have P is equal to say if the system voltage V1, V2 is the receiving end divided by the transmission line reactance into sine delta. This is the basic equation, and it will give the curve, power angle curve. This is the power, and this is angle delta, and it is going to become maximum at delta is equal to 90 degree. So this is the curve. Okay, so this is the value which is nothing but the P maximum, but we never operate our system near to the maximum angle. Otherwise, because of even minute disturbance in the system may come out from the synchronism, or it will be unstable. So this part is the unstable. It is unstable, whereas this part is a stable one. So we operate our system much more below then the calculated value, and it is called as a conservative criteria. So here the mechanical input to the prime mover and electrical output of the alternator is same. Means equilibrium position, it is operates say delta 0. So this is the operating conditions. So this is the basic which is needed why we are using the FACT devices. So FACT devices are used to modify the electrical characteristic of the transmission line to increase the power handling capacity as well as to improve the transient stability of the system. Now first we'll take the example of two machine system. We'll take the two machine system without compensation. Without compensation. So without compensation, say the transmission line, the reactance of the transmission line is X, and it is fed from one machine which having voltage V1, the second machine which having the voltage V2, and it is connected V1 and V2. Let here the V1 is equal to V2 and the reactance is X. So power P is equal to V square. Say this is equal to V square upon X into sine delta. And it become maximum. The power become maximum. So it is equal to P maximum into sine delta. What is the P maximum? Where P maximum is nothing but it become maximum when delta is equal to 90 degree. So P maximum is equal to V square upon X. So what would be the curve? The curve is very simple. Same curve is there, but we will draw again. So this is the power P and this is angle delta, and it will show the like that. So this is nothing but the P is equal to P maximum at sine delta at any value, whereas this is the P maximum. This is the P maximum, and we operate our system much more lower than the calculated value. Now, two machine system with compensation. Two machines system with midpoint compensation. We are using ideal compensation, and it is mount at the center of transmission line. So let the center of the transmission line, this is the reactance, which has two parts. The same reactance is there. Same assumptions are there. V1, V2. Again, V1 is equal to V2 is equal to V3. Sorry, V3 is V maximum. So let here we have connected shunt compensation. We have connected a shunt compensation at the mid of the transmission line. This is the shunt compensation, and the voltage is Vn. Okay. So under such condition, this reactance become X by 2. This reactance become X by 2. Total reactance is as it is V1, V2. Now here again we consider as V1 is equal to V2 is equal to V maximum at the center, and the power. I'm not going to discuss the entire derivation. Just I will write. In this case, the power P is equal to twice V square upon X into sine delta by 2. So it means that the power become P is equal to twice maximum, P maximum, because V square upon X, this is V square upon X, this V square upon X, this V square upon X, this P maximum is same. So twice maximum into sine delta by 2. So what is the meaning? The meaning is that the difference between without shunt compensated and shunt compensated line, we will draw again. So this is angle delta, this is power P, and earlier this is the curve which shows uncompensated line. This shows this curve is uncompensated. And the equation is P is equal to P maximum sine delta is the value. Okay, this is angle delta, and it is going to become at pi by 2 or 90 degree. Now, from this equation, it is found that the new curve become, it is the twice the maximum, and it is going to become maximum at pi by, it is pi. So here the delta by 2 means 1 pi by 2, it is pi, then it will be 90 degree, and it is going to become maximum. So what is the maximum value? This maximum value is equal to twice the P maximum. The maximum power that can be transmitted by the compensated line will be double. And whereas this is the earlier maximum value, is P maximum. So see here, even if you are operating our system much more below than the critical or say calculated value as per the conservative criteria, say this is the delta 0 at which our system is going to operate delta 0. If even same the conditions are this one, say earlier this is the delta 0, this is the power transmitted by the transmission line, but here with the help of shunt compensation, the power handling capacity of the existing transmission line can be increases. So the conclusion for this one topic is that the best location or the best location of shunt compensation is midpoint of transmission line. Okay, so the best location for the two machine system is the transmission line. This is a one say application of the shunt compensation. Now the second part of this one is that even we can increase, we can say prevent the second part, say we can say that prevention of end voltage support or the voltage collapse. Okay, this is the second part. So let the transmission line is a now a radial transmission line where the power is transmitted from one end and the load is connected at the second end. So instead of this one, this is the line, it is a radial line. It is a two machine system, whereas it's a radial line is there. Okay, so the reactance is X, voltage is V. Okay, and this is the voltage VR. This is the uncompensated line, compensated, and the same. If you want to do the compensation, we can connect here the compensations, shunt compensation over this one. It is the shunt compensation. So now, what is the difference? The difference is that if you draw the curve which gives the relation between power and the voltage, it is no doubt it is 100% voltage is there. It is in the form of rated voltage, and here say it is 100%. It is say 50% of the power. So under such condition, the curve which is depend upon the power factor, it is get collapse earlier, and it is depend upon the power factor of, say this is the power factor, this curve power factor is 0.85 lag, and whereas this is the unity power factor, It is a unity power factor, and whereas it is 0.95 lead power factor. So here the voltage is not equal, and it is going to collapse earlier because of the depend upon the power factor of load. Whereas for the compensated line, if the line is compensated with the help of shunt compensation at the near to the load, the same power P and voltage V, it is found that the voltages remain constant, and it is no doubt it is depend upon the load power factor, but the voltage profile is enhanced. So we can say that with the help of shunt compensation, which is connected to the near to the load, again it is 0.85 power factor, and say it is 0.95 leading power factor. So it is clear that here the voltage profile is poor, and here the voltage profile of the load is somewhat very good, and therefore the best location of shunt compensation for radial line is near to load, or it is also called as a load compensation. Now this compensation may be delivering the reactive power or consuming the reactive power. We'll see one by one. This is the second say advantage of shunt compensation in the transmission line. Now next we'll see one more advantage or the application of the shunt compensation is to avoid the which is called as a power oscillation damping. So it is a power oscillations oscillation damping. What is that? Whenever there is a sudden increase in load, or there may be some perturbation, that angle takes some oscillation, and after some oscillation, it is going to reach to the new equilibrium position. But this oscillation become very important if the system is very large and it is highly connected. We want the oscillation should be die out very early. It means the 1.5 cycle, 2 cycle, it should be die out. Otherwise, this oscillation may increase and come out the system from the synchronism, isn't it? What is that? Just with a small discussion, we can complete it. Say, for example, this is the initial position of the angle delta 0, this angle delta 0. Suddenly load increases, so it will take some oscillation, and after some oscillation, it reach to the new equilibrium position, say delta 1. But the second oscillation, this second oscillation should be smaller than the first oscillation. It means that the system is going to settle to the somewhere in the equilibrium. This is the classical model which we learned the power system stability. But if the second oscillation and it will take more oscillation, there may be chances that after few oscillation, the oscillation get increases and system become unstable, isn't it? So in the power oscillation also, the angle delta is continuously oscillate to its final value, and this due to this oscillation, this is the angle is there oscillation. Due to this oscillation, the power also get oscillate, and it is increase the oscillation in the transmission line or tie line power oscillation. So this is the power oscillation. Now, if you connect the shunt compensation, this shunt compensation provide the proper kVAR means the reactive power in the system in such a way that it pump the reactive power in the system in such a way that it die out the oscillations as early as possible. So because of this one, it will say take the new value of oscillations and it is die out earlier. So this is the DAM system. Similarly, it will occur for the power also, and it will die out the oscillation and the system become stable. So these are the some 3 points that which is the advantage or which is the application of shunt compensation. One more compensation advantage which is very useful, and we will see with okay. So the next point is the shunt compensation oscillations. Sorry, this is the shunt compensation, but transient stability, improvement of transient stability by shunt compensation. Shunt compensation. Say let the system is there. It is a. It may be as a. In short, we'll take this is the timer, and it is coupled with a system. It is a generator, and this generator is connected to the infinite bus. So this is the infinite bus. This voltage is EF at an angle of delta, having some reactance excess, synchronous reactance, and the current is I. Okay, and the mechanical input is PM, and electrical output of the generator is PE. So as long as your PM is equal to PE, the system is stable. It may be understood with the help of m d square delta upon dt square is equal to PA, that is the acceleration, and acceleration power is nothing but the difference of mechanical input minus electrical output. That is called as a swing equation. As long as this system is stable, means mechanical input and electrical output is same, just we will consider that there is no losses are there. Under such condition, the generator neither accelerate nor decelerate, and acceleration power is equal to 0. And whenever there is a disturbance or there is some fault in the system, there is a mismatch between mechanical input and electrical output, and acceleration power is going to exit in the system. We know that the mechanical input does not change in the transient condition. During transient condition, the mechanical input is remain same, and the automatic voltage regulator also remains same, and the transient stability is judged by the first swing. If the second swing is smaller than the first swing, the system is going to settle somewhere. The evaluation of transient stability is by the equal area criteria. What is equal area criteria? It says that if the area under acceleration curve and area under deceleration curve is equal, then the system is stable. Or simply, the acceleration area should be smaller than the deceleration area, then the system is going to stable anywhere, somewhere. This is the this one. So we are going to consider the equal area criteria. Equal area criteria. It means that the area under acceleration, area under deceleration should be equal to 0. The area under acceleration, it may be from delta 1 to delta 2 or whatever it may be the value. The acceleration area APA should be equal to 0. So what is that? Say this is the curve. which we have considered, P is equal to P maximum. P is equal to P maximum into sine delta. Okay, the same thing is there. This is the P maximum and all these things, say angle delta, and this is P. And we are operating over here. We are operating over here. Let the fault occur at this point. So the power output here, mechanical input is equal to the electrical output. Electrical output in the, if the fault occur over here, if the fault occur in this case, the area, the power output of alternator becomes 0, and whereas the mechanical input will remain same, so it will increase the speed or the mechanical input. So there is an acceleration area as long as here, suppose the circuit breaker opens, and the system again come to the operating position, but it will take some oscillation. So area under this region is called as the acceleration area. This is called as the acceleration area A1. And whereas it will oscillate, it may oscillate up to this maximum value. Let it is oscillate up to this one, and the area A1 become equal to the area A2, and if this is, so this condition exit, means area A1 is equal to area A2, the system is stable. And if your area A1 is greater than area A2, it means that the system is unstable. So this is the equal area criteria, and it is used to evaluate the transient stability. Now our objective is to examine the transient stability improvement with the help of shunt compensation. So first we will see the transient stability improvement with the help of shunt compensation. How would be? This is the uncompensated line. I'm not drawing the compensated line and uncompensated line diagram. Just we'll see the power angle curve for the earlier case. This is the two systems are there. Angle delta, power P, and here this is the curve for the compensated line. Okay, this is the compensated line which we have seen earlier. This is the P is equal to twice V square upon X into sine delta by 2. Just we have seen. And this is the curve which is equal to P is equal to V square upon X into sine delta. So this is uncompensated, this is compensated line. Now, say this is the operating position, and the fault occur. Due to fault occur in the system, it makes some area A1, acceleration area A1, and because of this oscillations, say this is the area A2. This is the area A2. Same thing is there, area A2. So this is the area margin. This is the marginal area that there may be a system may improve. So this is more area is there. Means, say for example, instead of opening circuit breaker here, it may open the circuit breaker at this point. So under such condition, the new area become this part. This part is the new area. So we can say that this angle is the critical clearing angle. If the circuit breaker is going to open later on, definitely the area A2 is smaller and the system will be unstable. So this is called as a critical clearing angle, and from the system data, one may calculate the critical clearing time. So that should be your critical clearing time should be greater than the fault clearing time, which includes the relay time, and circuit breaker times. Okay, this is the some protection point of view. Now we want to examine the power system transient stability improvement with the help of fact devices. So here it is a compensated line. It is a compensated line characteristic. Okay. So here, suppose the fault occur, it will remain, the power becomes 0. Here the fault is get cleared. So this is the area A1. This is the area A1. That is called as the acceleration area. Now, because of this one, it is going to jump to the up to this value, and somewhere it will complete the area A2, which is equal to the area A1. So this is the deceleration area A2. So we find here it is quite clear that this much is the total, this much is the area available again, even if the circuit breaker is going to open earlier later on, or the system may operate to the higher angle and it will transmit more area. So these are the marginal area to improve the transient estimate. So this area is very large, this area A2, AM2, and just I will write AM1. So the marginal area for uncompensated line, this is the uncompensated line, is very small, and whereas the marginal area for the compensated line is very large. So under such condition, one may examine that the power system can transient stability of the transmission line can be increased very large amount with the help of shunt compensation. So these are the some application of shunt compensation in the with the transmission line. Now next point is the controllable VAR generation. It means that whenever we are using the shunt compensation, it should be controlled. The amount of the power, amount of the VAR can be say controlled by some means. So there are two methods. One is the variable impedance method, where we are going to vary the impedance of capacitor or inductor to be connected. For example, this is the line, and here we have connected the parallel. It is a shunt compensation. We are discussing the shunt compensation, and we are going to control this value of the reactor somewhere, the current in the inductor IL. So here it is going to consume the reactive power because it is an inductor. So it consumes the reactive power, or in other word, we can say that absorbs the reactive power. Whereas if we connect the capacitor, so the current in the capacitor is the leading one, and it is going to generates reactive power Q, and here reactive power Q, isn't it? So here it is generated. So VAR generation, there are two words are there. One is the absorption. So it consumes the reactive power. So we can say that the absorb the reactive power, and whereas it deliver the reactive power to the transmission line. So it is a generate one. So the first method is a variable impedance method, where we are going to vary the impedance of inductor and capacitor with the help of thyristor valves. And second is the switching converter. Switching converter type VAR generation. We are using word generation, but it is both sides, is the generation and absorption. So there are two methods. Variable impedance method is there, and second is the switching converter VAR generations are there. And this variable VAR one, that is this one, it has a different part, that is a different category. One is the thyristor controlled reactor, thyristor switch reactor, thyristor thyristor switch capacitor, okay, and fixed capacitor, thyristor control. So these are the methods by which one may vary the impedance of the reactor and inductor, inductor and capacitors connected in the shunt to the parallel line. And in the switching converter type, it is a synchronous motor. We are using as a synchronous motor as a synchronous condenser. So synchronous condenser or compensator. Condenser, we are using synchronous motor as a synchronous condenser or the compensator. But the synchronous motor consumes the active power, and if the rotating part is replaced by the static one, so it becomes a static synchronous condenser, SSC, or compensator, or it may be statecom. So very popular statecom. So in the switching converter type VAR generation, we are going to discuss the static synchronous condenser or compensator, that is the statecom, with energy storage and without energy storage. Whereas in the variable impedance type, we will discuss the thyristor control reactor, thyristor switch reactor, and thyristor switch capacitor in the next lecture. So this is the summary lecture for shunt compensation. For now, in the next time, we will take this remaining part as a summary lectures.